Let G be an undirected graph, and let M be a subset of the edges. We say that M is a matching in G if no two edges in M are incident to the same node. So for example, if we look at the set M consisting of the edges A, B, and DE, there's a matching because no two edges in M are incident to the same node. But if we look at the set consisting of AC and BC, that will not be a matching because there are two edges that have C as an end node. Given a matching, we can categorize the nodes into two different categories. So if a node is not an end of a matching edge, then we call it M exposed. For example, the node C here is M exposed. The remaining nodes are called M covered. So here A, B, D, and E are M covered. And a matching M is a perfect matching if every node is M covered. For this graph, we can see that there's no perfect matching because there are an odd number of nodes. Because every edge in a matching covers two nodes, if there's a perfect matching, the number of nodes in the graph must be even. Given a matching M, a path P is called M alternating if its edges are alternately in and not in M. So for example, if this is my graph, and if these are my matching edges, then this path here is M alternating because the edges are alternately in and not in M. So this edge is not in M, this edge here is in M, this edge here is not in M, this edge here is in M. But if we take this path here, you can see that we have two consecutive edges that are not in M, so this is not M alternating. And if it happens that the end nodes of an M alternating path are M exposed, then what we have is an M augmenting path. Okay, so here P is not an M augmenting path because only one of the ends is M exposed. But suppose that we have the following. And if we look at this path, then this is an M augmenting path because both end nodes are M exposed. The reason why it is called an M augmenting path is because we can use this path to obtain a larger matching. And the way to obtain a larger matching is to simply flip the edges. So we take the edges in the path that are not in M and throw them in the matching and take away the original matching edges. So here you can see the result. So the red edges are my new matching edges and the black edges are thrown out. And it is possible that there's some other part of the graph there's a matching edge. So now, what is my matching? Well, my matching will be in red. And you can see that I have one extra edge in my matching than the original one. So one question that we're interested in is to find a maximum cardinality matching. In other words, a matching of maximum size. And it turns out that M augmenting path holds the key. So this is a theorem. A matching M is of maximum cardinality if and only if there is no M augmenting path. So one direction is easy. We have already seen that if there is an M augmenting path, then you can find a matching of larger size. So we're going to prove the other direction. And we're going to show that if there's no M augmenting path, then M is of maximum cardinality. And the proof is going to be by contradiction. So suppose that M is a matching, but not of maximum cardinality. That means there exists a matching N that has higher cardinality. And now we're going to look at the graph with nodes that are the original nodes of the graph and the edges formed from the symmetric difference of N and M. So the edge set is basically any edge that is in either N or M but not in both. What does this graph have to look like? Because no two edges of M are incident in the same node, and the same is true for N, that means that a node can be the end of an edge in N, or an end of an edge in M, or both. And so the edge sets of the components of this graph will be paths or cycles. And the paths have to alternate between n and m. So let me use a color here. Let's say m is red and n is blue. And if we have a cycle, the number of edges must be even because every edge must alternate between an edge in n and an edge in m. Now, in every cycle, the number of edges in n and the number of edges in m are the same. But we know that the number of edges in n is greater than the number of edges in m. So there must be a path where the number of edges in n must be greater than the number of edges in m. So we must have a situation like this. So one of the components of the graph has to be like this. And now we can see that this path is an m augmenting path because the ends must be m exposed. And so we have found an m augmenting path, and that's what we needed to prove. Even though this theorem gives a characterization on when m is a maximum cardinality matching in terms of the existence of m augmenting paths, it's not clear how we can always identify if there is an m augmenting path or not. And this is the key task in the problem of finding a maximum cardinality matching.